All right. So we are starting back somewhere close to where we left off last time. Everybody get all warm and cozy under your blanket. Turn on your fireplace. Get ready. Maybe put on some smooth jazz or something. That's not what you fall asleep to. Whatever music you fall asleep to. The sound of rain. And here we go. I'm going to read you a bedtime story about Ethernet. Yeah, I don't know if we actually left off right here at multicast and broadcast addresses, but as I said before, I think I'd like to just start here because I realized the other day I know what multicast means. I know what it is, and that's it. So, Ethernet plus multicast is an interesting thing to learn about. Anyway, here we go. Ethernet, the definitive guide, chapter 3 somewhere. All right, the Ethernet delivery mechanism also supports multicasting, which is more efficient than sending the same frames to multiple recipients. A multicast address allows a single Ethernet frame to be received by a group of stations. Okay, this is nothing new if you've done CCNA work. An application providing streaming audio and video services, for example, can set a station's Ethernet interface to listen for specific multicast addresses, in addition to the built-in unicast physical address. This allows for a set of stations to be configured as a multicast group, which is provided with a specific multicast address. A single stream of audio packets sent to the multicast address assigned to that group will be received by all stations in that group. Hello. Oh, I like that username. Inside Sources. That's cool. Uh-oh. Audio and video out of sync. Shoot. I don't know how to troubleshoot that on my end. Is anybody else seeing that? Because if so, I have no problem just ending the stream and starting it back up again. Okay. So Javier says it's in sync. Yeah, shoot. Sorry, Inside Sources. I don't know what to tell you. Maybe it'll eventually sync up. This happens sometimes with networks, as we've learned. Okay. Oh yeah, I remember this part because we talked about the dinner party in a dark room. Hilarious. Okay, we're just gonna go back over it. Anyway, the broadcast address, the 48-bit address of all ones, is a special case multicast address. All Ethernet interfaces that see a frame with this destination address will read the frame and deliver. God, I'm sorry. I can't read today. All Ethernet interfaces that see a frame with this destination address will read the frame in and deliver it to the networking software on the computer. After each frame transmission, all stations on the shared half-duplex network channel with traffic to send must contend equally for the next frame transmission opportunity. This ensures that access to the shared channel is fair and that no single station can lock out the others. Fair access to the shared channel is made possible through the use of the MAC algorithm embedded in the Ethernet interface located in each station. Sorry, my brain is processing that part of it. Contend equally. Okay. The media access control mechanism for shared channel half-duplex Ethernet uses the CSMA-CD protocol. Okay. The CSMA-CD protocol functions somewhat like a dinner party in a dark room where the participants hear but don't see one another. Everyone around the table must listen for a period of quiet before speaking, which is our carrier sense part of CSMA-CD. Once a space occurs, everyone has an equal chance to say something, so that's the multiple access, the MA part of CSMA-CD. If two people start talking at the same instant, they detect that fact and quit speaking. That's our collision detecting, the CD part of CSMA-CD. According to my therapist, solicited node multicast addresses are not real and cannot hurt me. Love it. To translate this into Ethernet terms, the carrier sense portion of the protocol means that each interface must wait until there's no signal on the shared channel before it can begin transmitting. If another interface is transmitting, there will be a signal on the channel. This condition is called carrier. Sorry about the zoom in. I think that's easier to read, right? Okay, historically, a carrier signal is defined as a continuous constant frequency signal, such as the one used to carry the modulated signal in an AM or FM radio system. There's no such continuous carrier signal in Ethernet. Instead, carrier in Ethernet simply means the presence of traffic on the network. The term originates from the Aloha radio system, discussed in Chapter 1, we remember that, from which Ethernet was derived. Alright, all other interfaces must wait until carrier ceases and the signal channel is idle before trying to transmit. This process is called deferral. With multiple access, all Ethernet interfaces have the same priority when it comes to sending frames on the network, and all interfaces can attempt to access the channel when it's idle. So we're talking about half duplex at the moment, in case that wasn't obvious. We're starting out with talking about half duplex, and we'll get into full duplex after this, according to the book. The next portion of the access protocol is called collision detection. Given that every Ethernet interface has equal opportunity to access the Ethernet, it is possible for multiple interfaces to sense that the network is idle and start transmitting their frames at the same time. When this happens, the Ethernet signaling devices connected to the shared channel sense the collision of signals, which tells these Ethernet interfaces to stop transmitting. Each of the interfaces will then choose a random retransmission time after which to resend its frames in a process called backoff. The CSMA-CD protocol is designed to provide fair and efficient access to the shared channel so that all stations get a chance to use the network, and no station gets locked out due to some other station hogging the channel. After every packet transmission, all stations use the CSMA-CD protocol to determine which station gets to use the Ethernet channel next. This seems fair and logical to me. None of this is difficult for me to understand. Oh shit, that's a goose. Hello. I'm not used to like Twitch things that happen, so all of this is new and wonderful to me. The emojis, I don't know if you call them that on Twitch, the little animated everything that you can do. It's great. Excuse me. I had spicy curry for dinner. And it's still affecting me a bit. Alright, collisions. If more than one station happens to transmit on the Ethernet channel at the same moment, then the signals are said to collide. The stations are notified of this event and reschedule their transmissions using a random time interval chosen by a specially designed backoff algorithm. Choosing random times to retransmit helps the stations to avoid colliding again on the next transmission. All of this makes a lot of sense. It doesn't seem too complicated. Oh my god, this is quite the page. It's unfortunate that the original Ethernet design used the word collision for this aspect of the Ethernet media access control mechanism. If collisions had been called something else, like distributed bus arbitration or DBA events, then no one would worry much about their occurrence. To most ears, the word collision sounds like something bad has happened, leading many people to incorrectly conclude that collisions are an indication of a network failure and that lots of collisions must mean the network is broken. The truth is that collisions are absolutely normal events on a half-duplex shared channel Ethernet and are simply an indication that the CSMA-CD protocol is functioning as designed. As more computers are added, there will be more traffic, resulting in more collisions as part of the normal network operation of a half-duplex Ethernet system. Collisions resolve quickly. For example, the design of the CSMA-CD protocol ensures that the majority of collisions on a 10 megabit per second Ethernet will be resolved in microseconds, or millionths of a second. Nor does a normal collision result in lost data. In the event of a collision, the Ethernet interface backs off, or waits, for some number of microseconds, and then automatically retransmits the frame. Half-duplex mode networks with very heavy traffic loads may experience multiple collisions for each frame transmission attempt. This is also expected behavior. Repeated collisions for a given packet transmission attempt indicate a very busy network. If repeated collisions occur, the stations involved will expand the set of potential back-off times in order to retransmit the data. The expanding back-off process, formerly known as truncated binary exponential back-off, that's a mouthful, is a clever feature of the Ethernet MAC protocol that provides an automatic method for stations to adjust to changing traffic conditions on the network. Only after 16 consecutive collisions for a given transmission attempt will the interface finally discard the Ethernet frame. I wonder why 16. Kind of sounds like someone was just like, I don't know, let's give it 16 tries, whatever. This can happen only if the Ethernet channel is overloaded for a fairly long period of time, or if it's broken. Nice, pretty, beautiful, lovely. No problems with that. Okay. What book is this? All right, let me make sure I can keep my spot here. Hang on. We're in chapter 3 somewhere where it says hardware. It is this book. You know what I'm going to do? I think for next time and future times, I'm going to take like a pretty shot of the cover of this book and just like leave it up so people can see, because I think that would be really nice to make sure people can see what we're reading out of. But yeah, this is the book that we're reading out of. It's called Ethernet, the Definitive Guide, Designing and Managing Local Area Networks. And this version was written and edited, well, written at least, I guess, by Charles Spurgeon and Joann Zimmerman. This is the second edition. I don't believe Zimmerman is on the first edition, which I made the mistake of ordering the first edition. So there's some stuff that's a little out of date in here, but apparently the second edition is actually the most recent version. Oh yeah, okay, thank you. Thank you, Fracticated. I love, man, y'all have the best fucking usernames. Let me get back to our page real quick and I'll talk for basic elements. Here we go. Yeah, I don't know where the fuck we were. I'm so sorry. Here we go. I think we're over here. Yeah, there we go. Thank you for the congratulations on the co-host gig. I guess I should say this like live now on my own channel. I accepted an invitation to be a co-host on the podcast, The Art of Network Engineering, which is incidentally the best network engineering podcast that exists. Definitely my favorite. I've been a fan of theirs for, you know, well, it's going to sound like not that long of a time because I haven't really been around on social media as a network engineer for that long of a time, but since I came on the scene last summer, they are the first group of people. Their Discord community was the first and really only one that I've been a part of for network engineering, just because there's so many great people in it. I don't need like a bunch of servers to talk to people. I don't need, an extra community other than that because it's so wonderful. Yeah, The Art of Network Engineering. They are a podcast with a bunch of awesome network engineers who host it, and I'm super stoked to now count myself as one of them. Yeah, they interviewed me over the summer, when I first maybe it was the fall last year, when I first sort of started being an idiot on Twitter. They, for some reason, wanted to talk to me about it. So I talked about my beginning as a network engineer, which wasn't that long ago, and what I'm up to. And I've been on this show a couple more times since then. One of the episodes I recently, co-hosted, managed was an episode with two other network engineer women. We talked about, the unique challenges and perspectives we have as women, specifically in network engineering, and how that can go. And that was a great episode. I did it along with Yvonne Sharp, who works at Google, and Micheline Murphy, who works, I think, for Cisco. I'm so sorry, Micheline, if I got that wrong. Pretty sure she works for Cisco. I've totally blanked. Anyway, they're wonderful ladies and super smart and way more experienced and better at their jobs than I am. So really, you should check them out. They're both on Twitter. But yeah, so that was another episode that I did with them, and then I was a guest co-host for actually one of their recent episodes, their goals for 2022. It was me and AJ and Tim. We had a good time talking about goals for this year. So yeah, so I'll be around on episodes with them doing the podcast, and we're also going to do some cool YouTube content, getting in there with all the different diverse sorts of, things we can do, shit with servers and network devices and all sorts of crap. So I'm really stoked to start doing that with them. We have an exciting year ahead, I'll say that. Thank you very much for the congrats. And thank you, Matt Bogenberger, for posting the Art of Network Engineering website in the comments. Yeah, they are an awesome podcast. Well, that's enough about me. Let's get back to this boring ass bedtime story about Ethernet. um Frick, where were we? Yeah, okay. So we talked about basically, all right, TLDR, collisions are not a bad thing. They're just part of the normal functioning of a half duplex Ethernet system. That's basically all we got to remember from here. CSMA CD is the protocol that ensures that, collisions are resolved and the network keeps doing what it's fucking supposed to do. End of story. So collisions are not a bad thing. They're just a sign that that's working. Of course, this is a half duplex. We're talking half duplex at the moment. So we're starting old and we're going to get newer as we go. Let's see. Yeah. So if we do happen to have a lot of collisions on a network, like way more than we might expect, we can actually do something called truncated binary exponential backoff. I'm shocked that there's not an acronym that follows that. Truly. TBEB. That's a great acronym too. TBEB. It rolls off the tongue. But anyway, it is a clever feature of the MAC protocol. It's part of Ethernet. So it's just another part of like adjusting for that random time after you have a collision. How long we wait to retransmit. And that's it. It's pretty simple. All right, hardware. So far we've seen what an Ethernet frame looks like. Let me scroll this over. And how the CSMA CD protocol is used to ensure fair access for multiple stations sending their frames over a shared Ethernet channel. The frame and the CSMA CD protocol are the same for all varieties of Ethernet, whether the Ethernet signals are carried over coaxial, twisted pair, or fiber optic cable. The same frame is used to carry the data, and the same CSMA CD protocol is used to provide the half duplex shared channel mode of operation. In full duplex mode, the same frame format is used, but the CSMA CD protocol is disabled because we don't need it, right? It's for detecting collisions, but when you've got full duplex going on, you don't have to worry about collisions being a problem. Now that we've seen how the Ethernet frame and MAC protocol work, we next describe Ethernet hardware. There are two basic groups of Ethernet hardware components: the signaling components, used to send and receive signals over the physical medium, and the media components, used to build the physical medium that carries the Ethernet signals. Not surprisingly, these hardware components differ depending on the speed of the Ethernet system and the type of cabling used. To show the hardware building blocks, we'll look at an example based on the twisted pair Ethernet media system. I wonder if I got to this last time. I truly don't remember. But I guess that just means we got to go over it anyway. The signaling components for a twisted pair system include the Ethernet interface located in the computer. We did go over this. All right. I started way, way back in this chapter, but it's all right. All right. So we have a twisted pair system is what we're calling this. We have the Ethernet interface that's located in the computer. We have a transceiver and the actual twisted pair cable. An Ethernet, if they say an Ethernet, I think they must mean like an Ethernet system, I assume. An Ethernet system may consist of a pair of stations linked with a single twisted pair segment, or multiple stations connected to twisted pair segments that are linked together with an Ethernet switch. Segments were linked together in the original CSMA CD half duplex Ethernet system with signal repeaters, also called repeater hubs. Modern Ethernet systems are based on Ethernet switches, which typically function in full duplex mode. Okay. None of this is like super mind-blowing. All right, so yeah, okay, I remember we got to this figure last time. Here's an example basically of a very simple Ethernet system, right? We've got our Ethernet switch. Not sure, can you not see my, I guess you can't. Simple Ethernet switch right here. RJ45 plugs, boom, boom. RJ45 jacks. Plugs into jacks. And that's it. I honestly, I don't know why they needed like a giant fucking diagram for this, but that's fine. All right. So we have two computers, or stations as we call them, connected to a switch using twisted pair cables. Each computer contains an Ethernet interface, which provides a connection to the Ethernet system. The interface contains the electronics needed to form up and send Ethernet frames, as well as to receive frames and extract the data from them. The Ethernet interface is typically provided as a set of chips built into the computer's main logic board. In this case, all you'll see of the interface is an Ethernet connector on the back of the computer. You can also purchase add-on Ethernet interface cards that plug into a card slot on the computer or an external interface, such as a USB port. The Ethernet interface connects to the media system using transceiver electronics designed to work with the twisted pair media. The word transceiver is a combination of transmitter and receiver. Most modern desktop and laptop computers include built-in transceivers for twisted pair connections. A transceiver contains the electronics needed to take signals from the station interface and transmit them to the twisted pair cable segment, and to receive signals from the cable segment and send them to the interface. Who's asleep yet? Snoring away. Prior to the integration of Ethernet electronics in laptops and desktop PCs, it was common to use an external transceiver for both twisted pair and fiber optic media systems, which connected to a transceiver port on the Ethernet interface. External transceivers are described in Appendix C, which we will not be visiting at this time. All right. Yada yada yada. Okay, we're talking about how it's connected. Like, we don't need all that. Media components are another part of an Ethernet system. The cables and signaling components used to create the signal carrying portion of an Ethernet channel are part of the physical medium. The physical cabling components vary depending on which kind of media system is in use. For instance, a twisted pair cabling system uses different components than a fiber optic cabling system. That makes sense. Just to make things more interesting, every time. A given Ethernet system may include several different kinds of media systems, all connected together using Ethernet switches. The design and operation of Ethernet requires that there's only one transmission path between any two stations, and Ethernet grows by extending branches in a network topology called a tree structure. A typical network design actually ends up looking less like a tree and more like a complex set of network segments connected to switches throughout wiring closets in a building. This is cute. Okay. None of this is like crazy news to me. It might be to some people, depending on your experience level, but yeah, I mean, like, this is typical. The resulting system of connected cable segments may grow in any direction and doesn't have a specified root segment. However, it's essential not to connect Ethernet segments in a loop, as each frame would circulate endlessly until the system was saturated with traffic. On an Ethernet system composed of segments connected with switches, okay, yada yada yada, spanning tree protocol exists, we got it. In the original half-duplex system, an Ethernet LAN consisted of network cable segments linked with one or more signal repeaters. Today, Ethernet systems are built using switches to connect multiple network segments together, with all of the segments usually operating in full duplex mode. In full duplex mode, each station has a dedicated connection to the switch port and does not share the Ethernet channel bandwidth on that link with any other computer. Network protocols and Ethernet. I'm falling asleep myself a little bit. Yeah. Now that we've seen how frames are sent over Ethernet systems, let's look at the data being carried by a frame. Data that's being sent between computers is carried in the data field of the Ethernet frame and is structured according to higher level network protocols. The high level network protocol information carried inside the data field of each Ethernet frame establishes communications between applications running on computers connected to the network. The most widely used system of high-level network protocols is called the Tcp Ip Suite. The important thing to understand is that the high-level protocols are independent of the Ethernet system. In essence, an Ethernet LAN with its hardware and Ethernet frames is simply a delivery service for data being sent by applications using high-level network protocols. The Ethernet LAN itself doesn't know or care about the high-level network protocol packet being carried in the data field of the Ethernet frame. Okay. Now we're talking best effort delivery. I think we may have stopped around here last time I streamed. This is a good place to point out that the Ethernet MAC protocol does not provide a guaranteed data delivery service. Ethernet does not provide strict guarantees for the reception of all data. Instead, the Ethernet MAC protocol makes a best effort to deliver each frame without errors. If bit errors occur during transmission, then a frame may be dropped. Ethernet was designed this way to keep basic frame transmission system as simple and inexpensive as possible by avoiding the complexities of establishing guaranteed reception mechanisms at the link layer. Okay. It's assumed that the higher layers of network operation, such as TCP IP, provide the mechanisms needed to establish and maintain reliable data connections when required. Okay, so Ethernet don't care. Ethernet's going to do its best, and that's all you can ask of it. Even so, the vast majority of Ethernets operate with very few bit errors or dropped frames. The physical signaling system is designed to provide a very low bit error rate. The details of how network protocols function are an entirely separate subject, yada yada yada, out of the scope of this book, skipping that paragraph. Whew! You know, I was really hoping we get to like some fun diagrams or something, but at this moment in time, we're still just sort of, oh, look, okay, we have something to look forward to on the next page. Couple diagrams. All right. Whew. Network protocols are easy to understand, says you, because we all use some form of protocol in daily life. For example, there's a certain protocol to sending a letter. Oh, okay. And I don't, just for a second, I don't mean to, I'm really not shitting on like basic networking subjects. You gotta have a foundation, and it's very important to go like review that stuff or learn it for the first time. Totally not shitting on that. However, going through the analogies of like what it's like to send packets is a little bit much for me, so I am gonna skip over some of this if that's cool. Ethernet speaks to me. I just do my best to. Me too, man. Just getting through it. Just doing my best. I disconnected my network cable and I think the token fell out and rolled under my desk. What do? You move your desk and you get that token. And then you take your network cable, you take the token, and you put the token back in. And then real quick, before it can fall out again, you gotta plug it back in again. It's alright, it happens to the best of us. Alright, so this goes through network protocols. Oh my lord. Okay, we're gonna have to skip some of that because I have done enough networking protocols for my entire life and I'm still not done with them. So let me have this one thing. All right. Oh, this is cute. All right. So this isn't even, this isn't even something complicated or interesting. It's really just like how a networking protocol works. That's cool. All right. Protocol encapsulation. So high-level protocol, I'm not even going to read this whole thing, I don't think, but high-level protocols basically are independent of the Ethernet system. They have their own rules and stuff that they follow. The Ethernet system doesn't give a shit about those, and the high-level protocol doesn't give a shit about Ethernet either. Everybody has their own addresses, and they just like happen to work together. At least that's how I would explain it. I don't know. Yeah, so we have a data field in the Ethernet frame, and that's where you're going to have your high-level protocol packet actually encapsulated within, right? Encapsulation is... Okay, I'll read this sentence because it's pretty good. Encapsulation is the mechanism that allows independent systems, like network protocols and Ethernet LANs, to work together. So frame encapsulating a packet, essentially. With encapsulation, the Ethernet frame carries the network protocol packet by treating the entire packet as just so much unknown data placed into the data field of the Ethernet frame. Upon delivery of the Ethernet frame to the destination address, it's up to the network software running on that station to deal with the protocol packet extracted from the Ethernet frame's data field. It's pretty cool. It's pretty smart. Like, if you think about it, when they were inventing all this shit, somebody had to have been like, let's just carry it in this like one field, you know? They don't have to care about each other. It's kind of cool. can talk about OSI again. I'm not going to talk about OSI again. This is a little bit different than how I started out streaming. I started out streaming explaining things to people who had no idea, as if people had no idea, but I'm assuming that most of the people who are watching me on Twitch know at least a little bit about technology. If you don't, nothing wrong with that. Just throw a comment in the chat or something. I'll explain it, but I am kind of operating under the assumption that we all know some basic things, like how encapsulation works, what a networking protocol generally is, that kind of thing. Okay, let me talk about having to address the packet and the frame, whatever, destination source addresses. All right, Internet Protocol and Ethernet addresses. High-level network protocols have their own system of addresses. Okay, we already know that too. I love this. Oh, this is so cute. The newer IPv6, which provides larger addresses, is being deployed in parallel with the existing IPv4 system. I don't know if I'd call it in parallel. I'd call it very contentiously and sometimes. People have extremely strong views on IPv6. Okay. Yeah, we don't need to talk about how it's like a 32-bit address and stuff. We know that. It talks about ARP. Ugh. It's always good to review ARP. And this is a cute little, even colored, like, diagram. So we'll review ARP. So cute. This computer, Station A says, I'm looking for the 48-bit Ethernet address of the host whose 32-bit IP protocol address is 192.0.2.2. And then Station B says, I heard that... Hang on. No, what have I done? I'm sorry. Took it out of reading mode. Station B says, I heard that broadcasted ARP requests, and that's my IP address. In return, here's my Ethernet address. This actually like makes it seem a little bit more complicated. I mean, it's fine. But yeah, like you know, ARP is learning the we're learning MAC addresses in relation to IP addresses, right? Because in order to send an IP packet over an Ethernet, system, you're using both that high-level protocol, the layer 3, and you're also using your Ethernet, protocol. So we have to have both the Ethernet way of addressing and also the IP way of addressing. So we have to associate them. Bam. Done. Okay. I'm not going to read through all of this. Although this is good to know, because the ARP request is sent in a broadcast frame, every Ethernet station on the same Ethernet LAN reads it and hands the ARP request to the networking software running on their station. It would have been, it would have been a better idea to use a specified multicast address for this purpose, so that only IP-speaking computers would receive IP ARPs, and computers running other protocols would not be bothered. The address resolution system in the IPv6 version of IP uses multicast addressing for this reason. Very cool. However, the ARP protocol was one of the first developed for this purpose, and the advantage of using Ethernet multicast addresses was not widely understood by all high-level protocol developers at the time. Excuses. Okay, so basically, it goes through this process. This is how we ARP, right? Hey, I have this, I'm looking for the MAC address of somebody with this IP address. The station broadcasts it out to the Ethernet, everybody in the Ethernet system, essentially, everybody on its layer 2 domain. And then whoever owns it says, oh, hey, got your message. That's my IP address, and here's my MAC address. And then Station A adds that into its ARP table, and we're good to go. Yeah, okay. The computers involved in ARP build a table in memory called the ARP cache to hold the IP addresses and their associated Ethernet addresses. Once this table is created by the ARP protocol, the network software can then look up the IP addresses in the ARP table and find which Ethernet address to use when sending data to a given IP-based machine on the network. reaching a station on a separate network. Okay, this is talking about routing now at a very basic level. I'm gonna move forward. Okay, looking ahead. This chapter has provided a brief introduction to the basic elements of an Ethernet system and how they operate. This description was based on the original half-duplex shared channel system, which was the primary mode of operation for many years. However, the development of full duplex Ethernet and Ethernet switches changed all that, and the most common mode of operation today is full duplex over link segments. In the next chapter, yada yada, it'll be full duplex. My God, we only just got through half duplex. All right, it's fine. You know what? It's fine. Here we go. Chapter 4. Everybody asleep? Everybody's sleeping? Got about 20 more minutes left in this stream, and then I'm gonna eat the rest of my curry. All right, we looked at the Ethernet system and how it works. We're going to take a more detailed look at the Ethernet frame and the full duplex mode of operation. You don't need to know all the details of the frame and Ethernet system operation in order to build and use Ethernets. So I guess they're using Ethernet as like a singular noun, as like a network, an Ethernet network. Ethernet, the Ethernet. It just sounds like so old-fashioned, but I do kind of like it. However, an understanding of these elements can certainly help when designing networks or troubleshooting problems. The original half-duplex mode MAC protocol was designed to allow a set of stations to compete for access to a shared Ethernet channel based on coaxial cable segments linked with signal repeaters. The half-duplex media access control protocol is based on carrier sense with multiple access and collision detection, aka CSMA-CD. The development of full duplex media systems made it possible for Ethernet links to operate in full duplex mode, providing a... That's so... What a weird fucking first half of this sentence. It's repeating itself. The development of full duplex media systems made it possible for Ethernet links to operate in full duplex mode. Well, maybe not. Media systems are different than Ethernet systems. Anyway, it provided a higher performance mode of operation than the one supported over shared channels using CSMA-CD. Full duplex is superior than half duplex. That's all you need to know. The auto negotiation protocol described in the next chapter automatically selects the highest performing mode of operation over a link, typically resulting in full duplex mode for Ethernet connections. Today, the vast majority of Ethernet links operate in full duplex mode, which we will describe in this chapter. However, half-duplex mode is still supported for Ethernet interfaces operating at 10 or 100 megabits per second over twisted pair cables, and you may find a station connected to a switch port over a link that's in half-duplex mode. Okay, Appendix B, which we won't visit at the moment. Little Lemur comes in and he tells us that a twisted pair link segment is capable of supporting full duplex operation by virtue of having two pairs of wires that support data being sent in both directions. So we have our transmit and our receive being used there. A station operating in half-duplex mode, while it's connected to a twisted pair media system, may indicate a misconfigured link or an issue with the auto negotiation system. Simplify the description of these elements. This chapter is in two parts. The first two sections look at the structure of the frame and the full duplex media access control system. The following two sections examine flow control and describe how the high-level network software in a computer uses Ethernet frames to send data. All right, that's the meaty stuff I want to get into. Let's do it. Frame relay was still on CCMP route 2 years ago. Oh, fuck. What year was first edition of this book? You know, I need to look that up because... Well, shit, I have it, like, right behind me. Hang on. Here it is. This is the first edition, which I made the mistake of purchasing. Luckily, the PDF is second edition, but where is the publishing date in a book? It's been a long time since I've looked for this. Well, it says copyright 2000, so that might give you something to go off of. Yeah, printing history, February 2000. The year 2000. The beginning of the year 2000 is when this book was published. So I don't know. It probably says in this PDF actually when second edition was published. Let's okay, I'm in page 44 it looks like, just to get back to, but now I'm super curious. History. There we go. Haha. Revision history for the second edition. All right, so 14 years later, we got the second edition. So, second edition, this PDF that I'm reading out of is definitely more updated than the hard copy that I have here. I can't believe I fucking bought the first edition. This is that old. I guess I can keep it as like, I don't know, a piece of history. I mean, I'm sure everything is like accurate and correct, right? It's just like fucking not got new Ethernet systems in there, so whatever. Like it's a good like introduction to it either way, right? Because whoop, I'm not gonna be like building Ethernet systems anytime soon. Like in my spare time or something. I just want to learn. Okay, back to page 43, wherever the hell that went. Let me try. Let's see. Where? No, we were in chapter 4, weren't we? Okay. The organization of the Ethernet frame is central to the operation of the system. The Ethernet standard determines both the structure of a frame and when a station is allowed to send a frame. The frame was first defined. Sorry, weird Zoom issues. There we go. The frame was first defined in the original Ethernet DEC, Intel, Xerox, or DIX standard, and was later redefined and modified in IEEE 802.3 standard. The changes between the two standards were mostly cosmetic, except for the type or length field. The DIX standard defined a type field in the frame. The first 802.3 standard, which was published in 1985, specified this field as a length field, with a mechanism that allowed both versions of frames to coexist on the same Ethernet system. Hang on, I gotta process that. My brain did not take that in. So the original standard, the DIX standard, had a type field. The 802.3 standard called it a length field. Oh, so that's why it's called type length. I bet. Type or length. Yeah, okay. So that first 802.3 standard called it a length field, but had a mechanism that allowed both versions of frames to coexist on the same Ethernet system. Most networking software kept using the type field version of the frame. A later version of the IEEE 802.3 standard was changed to define this field of the frame as being either length or type, depending on usage. Okay. So we've got a figure below at some point that's going to show the DIX and IEEE versions of the Ethernet frame. There are 3 sizes of frame currently defined in the standard, and a given Ethernet interface must support at least one of them. Okay, so remember, this information is all from like 2014, so take this as you will. The standard recommends that new implementations support the most recent frame definition, called an envelope frame, which has a maximum size of 2,000 bytes. The 2 other sizes are basic frames with a maximum size of 1518 bytes, and Q-tagged frames with a maximum of 1522 bytes. So here we go. Can I zoom in without? Nope. What is our first one? Let's see. It says there are 3 sizes currently defined. Let's see. So here, okay, I guess the title is underneath. So this would be the DIX basic frame. We had a minimum of 64, a max of 1518 plus our preamble. So that sounds like the 802.3 standard that I thought we had today. So with the preamble being 8 bytes, we have our destination address, source address, our type field, data, and then the FCS. So that looks very familiar to me. You know, that's basically what we have, I think. Underneath it, we have the IEEE 802.3 basic frame. So we also have a minimum of 64 bytes and a max of 1518 plus our preamble. But what the hell is this right here? Hang on, let me zoom in on that. Global/locally administered bit, individual group and address bit. SFD. Okay, I don't know what the fuck that is. And then below that, we have the same thing essentially. Basic frame, 802.3, but it's got a Q tag. So our Q tag is inserted between the source address and the length and type field. Yeah. So we have an extra, it's 4 bytes. So we add those 4 bytes onto our maximum of 1518, which becomes 1522. And then here, finally, we have the IEEE 802.3 frame with the envelope prefix and or suffix. So, yeah. Weird. I'm a little confused because I could have sworn when we were looking at the Ethernet frame earlier, it looked like this. But let's keep going. Because the DIX and IEEE basic frames both have a maximum size of 1518 bytes and are identical in terms of the number and length of fields, Ethernet interfaces can send either DIX or IEEE basic frames. The only difference in these frames is that the contents of the fields and the subsequent interpretation of those contents by the network interface software. All right. Does somebody who knows more than me know what the fuck is going on? Because I've never actually seen, like, a 7-byte preamble is interesting to me. Like, are these actually modern? Are these still in use by IEEE? Interesting. A detailed tour of some of the frame fields. All right. Oh, good lord. What are you talking about in the comments here? Y2K. Wow. Yeah, shit. I'm gonna have to get my CCNP one of these days. And then I'll have to recertify 3 years later. Sounds like a fucking joy. Alright, we're starting with the preamble, boys. Here we go. How much time we got left? I can do this in 5 minutes. Let's do it. The frame begins with the 64-bit preamble field, which was originally incorporated to allow the 10 megabit per second Ethernet interfaces to synchronize with the incoming data stream before the fields relevant to carrying the content arrived. The preamble was initially provided to allow for the loss of a few bits due to signal startup delays as the signal propagates through a cabling system. Like the heat shield of a spacecraft, which protects the spacecraft from burning up during re-entry, the preamble was originally developed as a shield to protect the bits in the rest of the frame when operating at 10 megabits per second. Very interesting. Lemur comes in and he tells us that the original 10 megabit per second cabling systems could include long stretches of coaxial cables joined by signal repeaters. The preamble ensured that the entire path has enough time to start up so that signals are received reliably for the rest of the frame. The higher speed Ethernet systems use more complex mechanisms for encoding the signals that avoid any signal startup losses, and these systems don't need a preamble to protect the frame signals. However, it's maintained for backward compatibility with the original Ethernet frame and to provide some extra timing for interframe housekeeping, as demonstrated, for example, in the 40 gigabit per second system. Again, this is from 2014, so I guess we probably have like some much higher speed Ethernet systems that we're not talking about here, but baby steps. While there are differences in how the two standards formally define the preamble bits, there's no practical difference between the DIX and IEEE preambles. The pattern of bits being sent is identical. So in our DIX standard, we have 8 octets or 8-bit bytes. The first 7 comprise a sequence of alternating ones and zeros. The 8th byte of the preamble contains 6 bits of alternating ones and zeros, but ends with a special pattern of 1, 1. These 2 bits signal to the receiving interface that the end of the preamble has been reached, and that the bits that follow are the actual fields of the frame. Oh, that's cute. So clever, so cute. Good job. In the IEEE 802.3 specification, the preamble field is formally divided into 2 parts, consisting of 7 bytes of preamble and 1 byte called the start frame delimiter, or SFD. Okay, so that's what that was. Up here in this diagram. Oh, sorry. Excuse me. Yawning. And this diagram over here, I was like, what the fuck's going on? So that's why we see a 7-byte preamble and then a 1 bit of the SFD. Okay. I think I really went down low there. There we go. Okay, so that's the IEEE 802.3 specification. It's divided into 2 parts. We've got 7 bytes of the preamble and then 1 byte called the start frame delimiter. And the last 2 bits of the SFD are 1 and 1, just like with the DIX standard. So they're basically the same. Like, there's very little difference between them, really. It's just that you have formal division in the IEEE standard versus like the DIX standard just like has those last 2 1 1. There's no formal division of anything, but in the IEEE it actually talks, I guess it specifies. It is very specific about having that last 1 byte be named and be special because of those 2 1 1 bits. Okay. All right, the destination address field follows the preamble. Each Ethernet interface is assigned a unique 48-bit address called the interface's physical or hardware address. That's nothing new. The destination address field contains either the 48-bit Ethernet address that corresponds to the address of the interface in the station, that is the destination of the frame, a 48-bit multicast address, or it's just the broadcast address. Ethernet interfaces read in every frame up through at least the destination address field. If the destination address doesn't match the interface's own Ethernet address or one of the multicast or broadcast addresses that the interface is programmed to receive, then the interface is free to ignore the rest of the frame. Here's how the 2 standards implement destination addresses. So in the DIX standard, we have our first bit of the destination address used to distinguish physical addresses from multicast addresses. If the first bit is 0, then the address is the physical address of an interface, which is also known as a unicast address, because a frame sent to this address only goes to one destination. If the first bit of the address is a 1, then the frame is being sent to a multicast address. If all 48 bits are 1s, this indicates the broadcast or all stations address. All right, and then in the IEEE standard, the 802.3 version of the frame adds significance to the second bit of the destination address. Okay, hang on, let me go back. Okay, so in the DIX standard, it's the first bit. In the IEEE 802.3, it is the second bit, which is used to distinguish between locally and globally administered addresses. A globally administered address is a physical address assigned to the interface by the manufacturer, which is indicated by setting the second bit to 0. That's interesting. Okay, good to know. DIX Ethernet addresses are always globally administered. Okay, so globally administered means that the manufacturer has actually assigned that physical address to the interface. If the address of the Ethernet interface is administered locally for some reason, the second bit is supposed to be set to a value of 1. In the case of a broadcast address, the second bit and all other bits are 1s in both the DIX and IEEE standards. So there's not like a ton of difference I'm learning between the DIX and the IEEE standards. Lemur tells us locally administered addresses are rarely used on Ethernet systems because each Ethernet interface is assigned its own unique 48-bit address at the factory. Locally administered addresses, however, were used on some other local area network systems. Now, this is from 2014. I don't know if this was a thing back in 2014, but I know today you can set your, like, at least your PC and some other devices to, like, have dynamic MAC addresses. And I haven't really thought very hard about that before, but I'm curious how that process works and the ramifications and impacts of that. All right, kiddos. If I haven't put you to sleep yet, you're not going to sleep. So thanks for joining me. We will pick this back up. What page are we on? 47. Man, we are just going slow through this book, but that's okay. So we're going to pick up back at understanding physical addresses a little bit more. Hopefully get through chapter 4, maybe hit chapter 5 in my next stream. I should be streaming on Friday night. I'm scheduled to do that at 8 p.m. Central, 9 p.m. Eastern, 6 p.m. Pacific, US time. So join me then. And please, dear God, if you know more than me on any given subject, which I guarantee you do, come into the comments and school me. I'd love it. Anyway, until then, I hope you all have a great week, a great evening today, or a great morning if you're on the other side of the ocean. Just have a great whatever. Okay?